Last talk we have seen that there are basic axioms that are easy to get in order to establish the six functors formalism. These were the existence of functors base change, direct image, and some sharp operation for a subcategory of for a class of morphisms. And so I call these the category satisfying these axioms pre-motivic, because the idea is that from these axioms we can derive the full motivic formalism or a six functors formalism. As we will see also, the motivic homotopy category is a kind of initial object which satisfies this property, so it also justifies this strange terminology. So last time I had no time to finish this formal part, so I will end up the series with a notion of morphisms for this category. So let's say functoriality. This is important for several things, for the constructions and also later for realization. So we give us M, N. So recall S is a category of schemes. And essentially, pre-motivic categories are pseudo-functors to say to some monoidal to the monoidal categories, pseudo-functor. Which corresponds to the F upper stars. I don't recall the axiom. So what will be a morphisms from M to N? So first we have a data for, right, so for any x in S, for any scheme, we give us an operation which we denote phi upper star from M of x to N of x, which is monoidal, and such that for any morphisms in S, there is an isomorphisms like that. So I should write here the pullback for N, here the pullback for N, but usually it's clear from this notation. Okay. In other words, we have a natural transformation of pseudo-functors. But we also ask for other things. So in this context, as we have already seen, we always ask for adjoint. So here we ask that phi upper star admits a right adjoint. This is what will happen in practice. Phi lower star, so this also justifies in some sense this notation. Again, we will have some exchange transformation. So assume that P is a P morphism. So for example, smooth. In the rest of the talk, this is what we will get. And we can construct an exchange transformation. Maybe a recall. So this is P sharp phi upper star. We go P sharp phi upper star, P upper star, P sharp. So here it's taken in N and here it's taken in M. Then we use these isomorphisms. P sharp, P star, phi upper star, P sharp, and then, so this was the, the unit of the adjunction, and here we use the co-unit, and this goes to phi upper star P sharp. And the requirement is that this is an isomorphism. So morphisms are supposed to commute with P lower sharp. So that also justifies this notation. Maybe there's a kind of principle in this formalism that all left adjoints will always commute, and reciprocally all right adjoints will always commute. on the other end, showing that some left adjoints commutes with some right adjoints is usually a theorem in this field. Okay, so let me give you some quick example before going to the rest. So there are many examples of such morphisms. So, for example, we can, if we take again the example of sheaves, we can change topology. So, example, one of the main examples that we will consider is the functor which goes from Nisnevich sheaves. Say, let's take P equal SM, and it goes to the category of étal sheaves on smooth side of R. So this will be, say, I don't know, maybe rho upper star, and it will have a left adjoint. So this functor, just forget the topology, and this one takes a sheaf and take the associated étal sheaf. So you can check that this is actually a morphism. So maybe kind of terminology. I will say that phi star is an adjunction of primotivic categories. Or morphism, so that depends. Okay, so sorry, and if you use the model category that I defined, then it's easy to show that these adjunctions can be derived and induce also a primotivic adjunction at the level of derived category. Maybe there's also another interesting point is that you can enlarge the site which you look at. So maybe I should, let's write again rho. So if we look at the natural inclusion SNS sheaves from smooth schemes of finite type to schemes of finite type over some base scheme S, let's call it rho. This is an inclusion of sites, and you always have a functor like that. So you can look at sheaves for some topology on this big, very big site. And you can always restrict this to the category of sheaves on the smooth side. And it formally happens that this functor admits a left adjoint. So here the notation is slightly different. So we'll use rho sharp to denote the left adjoint. I'm sorry. But still, so here this category is the class of morphism is the category is the class of finite type morphism. But you can still consider that it's the class is SM, and you get here a primotivic adjunction of, say, SM primotivic category. So this means that the rho sharp here will commute with upper star and lower sharp if for P a smooth morphism. Okay. In the end, so this can also be derived. Like that. And a funny fact is that this functor is fully faithful and exact. So at the level of derived category, let's say I should write something like that. This functor is still fully faithful and exact. So that the category that you look that you obtain by looking at the smooth side is inside the other one. Okay. So this category is too big to get to satisfy the 6 functor formalisms, but still it's useful from time to time to go into this big category, because, for example, the CDH topology or the H topology is defined on this side and not on this one here. Okay, so if you want to use CDH or topology, then you can do that by going here. Okay. Okay, so I've finished now with the formal part of the talk, and I'll try to show that from these simple axioms you can derive a kind of geometric, you can get some geometric facts and intuition. So now in all the talk I will fix T, a triangulated motivic category. So here S is a category of scheme, a suitable category of schemes. So I recall usually Noetherian finite dimensional, and P, the class of morphism for which I get the operation P lower sharp, is the class of smooth morphisms of finite type. Okay. And just for comfort of the talk, I will assume that T is the homotopy category of some model category. M is a pre-motivic model category. This is just to be able to speak about homotopy colimit without making without having too many problems. Okay, so from that you can do some geometry. So I will introduce further axioms on the category T, so that in the end we will finally be able to formulate the theorem of cross functors of Ayub. And maybe a little bit more even. So I first start with the basic axioms that here we all know. So these are the axioms that are more or less forced by the construction of a stable homotopy, motivic stable homotopy category. So first of all, I remark the following. So there is a link between the functoriality and the classical consideration that we have. So let's consider any smooth morphism like that. Then I can define the motive of X over S. So usually I should denote that with coefficient in T as being the following object. This is P lower sharp, P upper star of a unit object in T. Okay, so in this talk I will just denote this ms of x without reference to by abuse or notation. So, and we call this the pre-motive of x over s. Okay. So first of all, this is a homological motive. So how do you get that? So it means that it's the dual or the weak dual of cohomology. So it's just to illustrate the axiom. So why is that? If you want to compute this functor over any object k, then you can write it as P sharp unit object tensor P upper star of k. So I write equality, but this should be isomorphism. Then we have the smooth projection formula. So this is the same thing as P sharp 1s tensor product of k. So here I have this exchange isomorphism. I just write equality, if you don't mind. So this is just an Sx tensor k. Okay, so this means that this composite functor is isomorphic to tensor product with the primotive of x over s. So just by adjunction, it means that K is any object in T of S. It's just some formal parameter. What?
It should be 1 unit.
Which one?
No.
Yeah, sorry. That's right. Thanks. Yeah, and so this is P sharp P upper star 1 of X, because P upper star is monoidal. 1 of S. Okay, thanks. So just by adjunction, this means that P lower star, P upper star is right adjoint to this tensor product. So it means that this is the same thing than internal Hom and Sx 1x. So okay, sorry. In other words, P star of 1x, if we apply this with k equal 1s, is the same thing as the internal Hom. So this is called usually the weak dual. This is not a strong a dual in the strong sense. It's just and this is what usually we consider as cohomology, as internal cohomology in category of sheaves. Okay, so there are formal properties satisfied by this primotive, which is the usual one that we know for, let's say, usual motives, or even for object of stable homotopy. Just a remark: if T is the derived category of sheaves, then the motive of X is just the sheaf, the free sheaf of R modules for the topology T represented by X. Okay, and maybe I should do that if we use the stable homotopy, which will be introduced, I guess, in the next talk. Of X, then MSX is what we usually denote as sigma infinity X plus. Okay. So the axiom that you can easily derive from, the properties of this motive that you can easily derive from the axioms of a primotive category are the following. First, MS of X is covariant in X. It's not so easy, but you can do it using especially this this here. You get also a Q-net formula in some sense. This comes from the smooth projection formula. Yeah?
So you're an argument that this is a computation, right? You define the motive of X over S as this way.
Yeah?
You already have that start of the unit, then you just check that this is
You check the example, you mean?
Yeah.
Yeah. This comes from the definition of the functor P upper star in the stable homotopy. So, yeah. This is just a computation. Okay. So, and also you get this property. So maybe this is Ntx cross St. And if P from S to S prime is smooth of finite type, you get P sharp MS of X is just the motive of a primotive of S prime given by a composite. Okay? So more or less this is what Oliver told us how you define this functor in the category of sheaves. Also, maybe I should mention that these functors are left adjoint, so they commute with homotopy colimits. And in the usual category, any object of, say, for example, of SH is a homotopy colimit of object like that, twisted by the Tet twist. And so this formula actually homotopically determines the functor F upper star. Okay. What?
Can you repeat the last sentence?
I'm saying that these properties of F upper star, if you usually determine uniquely this functor in categories like that. In category of sheaves or derived category of sheaves of simplicial sets or abelian groups and so on. Okay. So with this simple trick, this abstract definition here, we can already do some geometry and state the basic axioms that we know, which are fundamentally stable in motivic homotopy theory. So my first axiom is the homotopy property. So maybe if I just property A1 homotopy property, and it just says that for all skip S, for all x of S, as the canonical map is an isomorphism. So given by a projection of the affine line. Okay, this can be restated in terms of just functoriality, bare functoriality, using these isomorphism here. So it says that the co-unit map P sharp P upper star to identity is an isomorphism, or equivalently dually that this is an isomorphism. Okay, so you have a functorial interpretation and a kind of a geometric one. Okay, so obviously this leads us to our example. So usually we denote dA1 T effective, or there's also this notation by Joseph Ayoub of S. Just to be, you take the derived category of sheaves for topology T on smooth S, and you take the quotient by the subcategory so this means full triangulated subcategory stable by infinite sums, so it's called sometimes localizing subcategory. Okay, then it formally follows that actually this category you can perform this localization procedure in the level at the level of a model category, and so you will get the A1 local model category and the category of complex of sheaves like that. And you using this localized model category, you can show that all the functors that you want can be derived. So actually this gives again a pre-motivic triangulated category. Tensor product also can be derived, which satisfies, by definition, by construction, say, the homotopy property. Just a remark. By contrast, if you use the derived category of sheaves for the étale topology on the small site, with say coefficient, torsion coefficients, and invertible on S. First of all, I've not said that, but the pre-motivic structure on this category is hard to get. So you can show that P upper star for P smooth admits a left adjoint, but this is already a theorem. And also the A1, the homotopy property is also a theorem. So the homotopy property is implied by the so-called study of acyclicity morphism. So actually you can reinterpret, so this is proved in SGA4 by Artin, and actually you can reinterpret the homotopy property is the essential tool that they use to prove the smooth base chain formula in SGA4. So, okay, just to... For us, working with big site, it's essential to make the affine line contractible, and in some sense, it turns this big site here into something more reasonable. Okay, for the other axioms, P over axiom is stability, so I just recall take twist. I can define this object just to be a motive P1 of S modulo the motive, say, of the infinite point. So this gives a direct factor of this category, and so because the category is triangulated, this co-kernel exists, and I should translate it by -2 like that. So actually you see that the collection of these objects here for S schemes defines what is called in the language of fiber category, defines a Cartesian section of T seen as a fibered category over S. This means that for any morphism, say T to S, we are given an isomorphism like that. There's another example which is trivial of a Cartesian section like that. You can consider 1S shifted n times, even or any integer. And this is again a Cartesian section of T over S because the F upper star are triangulated functors. So we can abstract this situation, but I will not do that here. We can give us a set of Cartesian sections, which is the important thing is that it must be stable under tensor product. So here I can take n for any integer n positive, for example, and this will work the same. What? Positive. Yeah, positive now. In a minute I'll come to that. Okay, and maybe an important axiom of this category, an important property of this category T is the following. So I don't do the abstract definition, but I do a definition in a particular case. We say that T is Tate generated or generated by Tate twist. Maybe I should if the family of functors on MSX twist n shift I for x over s smooth and n positive here I in Z, is this family of functor is conservative. Okay, so this is already interesting. In some sense, you see, if you replace here, maybe just some philosophy now. If you you take any object E in T of S, so now I change the notation, then you can write E y n of x to be this. E as usual, and this is the cohomology represented by E in T. And this axiom here says that the object E is determined by its cohomology. So this is usually what we expect.
Do you use n or minus? I or minus?
Ah, sorry. That's right.
If alpha I and yeah.
This is the homology.
Homological notation.
Yeah, this is homological notation. Sorry. Thanks a lot. But in a minute, I'll give you the link with cohomology. No, well. This should be minus I minus n. Sorry, and it's really cohomology, but here I'm slightly. Because I've not stated my second axiom, I cannot take n to be negative here, but okay. So this is really cohomology which determines if. Okay, and actually there is a more important notion than just state generated. We will say, should I write? Maybe I. Important notion is that we say that T is well or respectively compactly Tate generated if moreover, so if it is Tate generated and the family MS X N. We could put Y here. Is every object like that? Sorry, is compact. Alpha compact for some ordinal alpha. And but here we just say compact. For compactly generated, compact means that the ohm from this object to commutes with infinite direct sums. So this is for us, this is the important thing. Most of the categories are compactly Tate generated that we will consider. This assumption, well Tate generated, is useful if you use the étale topology. As Oliver said, it's not reasonable because of the absence of finite cohomological dimension in general, but we still have this assumption in general. Okay, and if you have this, it implies that any k in T of S is the homotopy colimit for certain family of object like that, MSXI and I maybe So the category T of S is generated in a strong sense by these objects. Okay, now what about the main axioms that we will need in order to get the six-functor formalism? It's the stability axiom. So this is my axiom 2. There will be 4 axioms. So sometimes I denote it tab, and it just says that for any scheme, for any base scheme S, the Tet twist is tensor invertible. So that maybe, yeah. So maybe a remark and a warning. I should have inverted my definition. In all the definition of Tet generated that I have put here, if you satisfy the stability axioms, then Tet generated means for any twist n in Z. You have to take into account the negative twist. Okay? And so in particular, the category T of S will be generated by this object here, but for take and in Z, and this is really important. What? The remark is just to say that under these axioms of stability, you have to modify my definition of Tet generated, and instead of taking positive integer n, you must take any integer, and especially negative integer. Okay, so maybe I quickly give you some application of this axiom. This is for related with the notion of strong duality. So in my context, an object K in T of X will be said to be is strongly dualizable or rigid. I just write rigid because it's shorter. If the canonical map K, internal K1 of S tensor L goes to internal K to L is an isomorphism for all L. Okay, so by adjunction you can build this map just by adjunction from the unit map of the internal from the evaluation map, and you ask that these maps are all isomorphisms. And so a direct consequence of the axioms 2 is that of stability is that so the motive of P1 of S is a direct sum of 1S, 1, 2. So this object is obviously rigid. This one is tensor invertible, so it's also rigid. You can check that. And a finite sum of rigid object is rigid. So stability implies that this object here is rigid. With a bit of effort, here, you can show in fact that the homotopy axiom, the stability axioms plus something implies that the motive of any projective space is rigid. So maybe I should state another property. So I will say that T satisfies the Braun-Gerstens property, satisfy BG, if something that we have already seen for any distinguished square U X V W J P. So a Nisnevich distinguished square, like we have seen in the talk. Of Oliver, then the square here, WSB, is homotopy Cartesian. So this means that we have the so-called, or maybe I write it for those who have not seen that. This means that we have a distinguished triangle like that, SU. Here there is a boundary. And so one of these maps is the difference of the two maps here. Or, okay. Distinguished, sorry, triangle. Okay, these two properties are equivalent in good category. So once you have this axioms, you can prove the following. I don't know, maybe I'll leave this as an exercise. If T satisfies the homotopy property, stability property, and the Braun-Gersten property, then for any E of S vector space, the motif, the pre-motive of P of E, the associated projective space over S, is rigid. So you have to be a bit clever because for motives, this object here will be a sum of Ted twists, and so using the same argument, and here you can conclude. For in the stable homotopy category, for example, it's not so easy because you don't have a projective bundle formula, but still you can use the fact that being rigid in this context is stable under finite sums and also under finite extensions. And using that, you can cook out and prove this by induction on the dimension of this. Okay. So as you see, we are here. Maybe I should give the main example of stable category. Again, this is a category which is constructed for the sake of this property. You take again, let's say, dA1T effective category, which is the homotopy category of a model category structure on the category of complex of sheaves. The A1 local model structure, Nisnevich A1, T local, A1 local model structure. Then there is a procedure using symmetric spectra with respect to the object 1S1. For example, you can take other objects, then we can construct a universal category where this object is a tensor invertible, so we denote it dA1T SR. So this notation is from Morel, or say dA for topology T, with an adjunction dA1 effective SR of triangulated category. So this is the infinite suspension with respect to the Tet twist and the infinite loop space functor. So the universal property is that sigma infinity is monoidal and sigma infinity 1S1 is tensor invertible. Okay, so this terminology should not be taken too seriously because it cannot be a true universal property, like this category is the initial object of some category, cannot be formulated in terms of model category. It could be formulated if you use infinity category, for example. But still, this is the idea, and the construction is explicit of symmetric spectra. This is the first one of the Shipley. And Schwieder, which have first designed this category for arbitrary monoidal model category. Or even what? What? Say it again. Really?
Yes.
Not so. Okay, sorry. And actually, Ove already described the category, the construction of SH in these terms. Okay, and we'll see maybe in a minute or in some minutes the same construction for the stable homotopy category. Okay, so the remark is that the pair of adjoint sigma infinity, omega infinity defines the pre-motivic adjunction. So in this formalism, it will be really easy to get these kinds of transformation. So this means that I recall sigma infinity commutes with F upper star and P lower sharp, and is monoidal by construction. Okay. So this was the link with geometry. Now I'm starting to, in the 10 minutes that I have, I will try to give you more the two other properties. I mean, the one property that remains will be on Wednesday, but there is an intermediate property that helps you, or more or less it is equivalent to getting the F lower Schritt functor. So maybe this is the second part. Deglise method to get the F lower Schritt. So again, I will use some exchange transformation. Now we are back to the functorial point of view. So let's look at another exchange transformation. This time we consider a Cartesian square. Y, V, so P, Q, J, and K. And I want, let's write it delta. I won't define it to you. I leave this as an exercise. So there's an exchange transformation between lower sharp and lower star, which goes like that. This is the same procedure than we have seen before. Okay. What? Sorry, I put J is open. J is an open immersion, so in particular it is smooth, but there's no, for the definition of this transformation, there's no assumption on P. So, definition, this is the condition that we need to apply. This is called the Deglise method. We say that T satisfies the support property if two things. First, T is, we will say additive, meaning that T of the disjoint sum of some schemes is naturally isomorphic to the product of category by the obvious maps. Secondly, we ask that the natural transformation like that, delta sharp's lower star, is an isomorphism for any P, any square delta, such that P is proper. Okay. So once you have that, you will be able to glue the functors J lower sharp for J open immersion and P lower star for P proper. I just need some preliminary facts. In the construction, there will not be Cartesian square, but commutative square in general. So, but still, under this assumption, we can still we can exchange this isomorphism to the case. So here, if delta is Cartesian, I said this, but you can extend this just assuming that delta is commutative. If delta is commutative, P proper, what you get is that you can divide the square like that, u cross x, y. And what happens is that the map L here, L is, first it's an open immersion because these two maps here are open immersion, open, But it's also a closed immersion because Q and P prime are proper. So L is an open and closed immersion. And you can check that because T is additive, you can check that in this case it implies that L low sharp is isomorphic to L low star.
It was also supposed to be proper.
What?
Q was also supposed to be proper.
P? P prime here? Q? Ah, yeah, sorry. That's right. P proper. Absolutely. So L low sharp is isomorphic to L low star by a canonical map, and then in this case you can extend the natural transformation like that. So this is J sharp Q star Q prime star L star. You use this isomorphism here. L sharp. Then you use the exchange for this square here, say prime. Star Q prime sharp, L sharp, and this is the same thing with P star, K sharp. Okay. Okay, once you have that, you can just apply the construction of the line, which is explained in SGA4. Maybe I call this a theorem. So if T, so it's not exactly stated like that by Delin, but the method that he gives just apply. If you just have this assumption, then for all f, y, x separated of finite type, there exists f low shriek from T, y to Tx such that f shriek is equal to f sharp if f is an open immersion and f shriek is equal to f low star if f is proper. And besides such that let's say that and there exists a pseudo-functor structure T low shriek from S to cat. On one morphism is just given by F low shriek, which extends in the correct sense the transformation X delta sharp star above or on the right actually. Okay. So I have not much time to state that. The point is, maybe I should do it anyway. the main advantage of this method of Deligne is that any separated morphism of finite type admits compactification. So if we take F separated of finite type, we can introduce C of F, the category of compactification. So given by F from Y to X, given by the factorization of F like that, P is proper, and J open. Morphisms are given by morphism in X bar, which are compatible with G and P. And so you can prove that this category is non-empty and left filtering. So now you can, if you have such a factorization of F, you can put F lower shriek is equal to P lower star G sharp. Using this exchange transformation, you can see that this actually defines a functor from the category of arrow from Y to X to the category of arrows from dy to X. Functors in CF. And then you can define F lower shriek as the co-limit of these arrows, and so it's well defined. It's unique. And then by construction, you check that all these properties are true here. Okay, so the advantage of this approach is that you can just assume that F is separated of finite type. In the original approach of Voevodsky and Ayub, you assume that F is quasi-projective, but okay. Okay. So, but the question is that in general, it's very hard to get this property, this support property, which is, even in SGA4, for example, the support property is deduced from the proper base change theorem. The only way we can get it is by using another axiom that I will introduce on Wednesday, the so-called localization axioms. Okay. Yeah, I think I will stop that because otherwise I will go too far.
Is there any questions or comments?
All right. Yeah.
Thank you very much for your talk. And maybe I have missed who is the author of these two basic axioms? What is their origin?
Of these axioms here, formatted like that?
Who is the author? And also, would you like please to give us the simplest example where these two basic axioms are satisfied?
Which axioms? I state three axioms: homotopy, stability, and support property. So the support property. So the support property, we introduce it with Szynski to formulate this theorem. But so it appears, of course, in SGA4, it's underlying the method. So we introduce these axioms. The homotopy and stability were introduced by Voevodsky. And so as I said, the only example, there's no easy example where you can prove support property directly. The only way you can get it is by using either the proper base change theorem. You can show that this proves the exchange is an isomorphism, or using localization. I will explain that on Wednesday, how you can deduce. So localization is the existence of localization distinguished triangle, and you can deduce from that and the homotopy axioms and stability. You can deduce the support property, but going slightly, yeah. Actually, I have not checked that, but maybe for coherent sheaves, this is easier to get. I'm not sure. I should check. Maybe for the derived category of coherent sheaves, it's easier to get this support property. I have to check.